For this video, we're going to talk about the first derivative test. The first derivative test puts more information towards those critical points. So we talked about critical points for the last lesson, which is basically where the first derivative is either 0 or undefined. What the first derivative tells us is if this point is going to be a min or max, or if it's not even an extrema at all. So ways to look at that is if f prime of x changes signs from positive to negative, that means that point C is going to be a local maximum. And keep in mind what this is telling us. So the first derivative is the slope of our curve. So if our slope starts out positive and then it hits 0 at the critical point, and then it turns back down to negative. So if we start out positive, hit the critical point at 0, and then it starts going back down again, that means we're going to have a local maximum. We're going to have a top point. This pretty much follows the same rules if it's a minimum. If the first derivative changes signs from negative to positive, that means at that point C, at our critical point, it's going to be a local minimum. Again, the first derivative tells us the slope of the curve. If it's negative, it's going down. If it's positive, it's going up. So that means we're going to have a local minimum. And this doesn't seem too extraordinary. If neither of those occur, that means there is no min or max. So to do the first derivative test, we're going to first find our critical points. We're going to test a number in between those intervals to see if it's increasing or decreasing, or neither. And that's going to tell us if it's a relative min, relative max, or absolute min or max. Alright, here's a problem where it says find the critical points, what intervals is the function increasing or decreasing, and where are the local min or max points. So, we have our f of x. So to find our critical points, we first need to find the first derivative. So our first derivative, just a very simple derivative here, we got 2 minus 2x. Okay, to find the critical points, we need to see where that is equal to 0. And that is going to be when x is equal to 1. Okay, so now let's set up our interval. We have our number line here. We have a critical point at 1. And that's our only critical point. So now we got to test intervals from numbers on this side, and we got to test numbers on this side. Okay, so those are our only two intervals. We just split our number line in half. So pick a number on this side, plug it into our f prime of x. If it's increasing, if it's positive, that means it's increasing. If it's negative, that means it's decreasing, obviously. So let's pick a number. I'm just going to pick 0, just because that's the easiest one to the left of 1. F prime of 0 is a positive number. I'm going to pick one to the right of 1. I'm just going to pick 2. Okay, and f prime of 2 is going to be a negative number. So we went from positive to negative. That means our derivative graph went like positive to negative. That means we have a local maximum. At x equals 1. Now they said point, so I'm assuming they want us to find the coordinate value. So I'm just going to plug it into f of x, and we're going to get 1, 1. Okay, so this is our answer. Alright, ladies and gents, this one is asking the same thing, except I didn't list out the steps for you, and it's a little bit more tricky. So I'll determine the local minimums and or maximums for this function. So we're going to apply the first derivative test, because that will tell us if we have any min or maxes. So the first step in the first derivative test is to find the first derivative. So we have f prime of x is equal to, alright, so we have x squared minus 3 times e to the x. So we're going to have the product rule here. So I'm just going to apply the product rule real quick. So we have the derivative of the first, which is just 2x, times the second plus the derivative of the second times the first. Alright, that's pretty cut and dry. Now we want to see where our first derivative is equal to 0 or undefined. I forgot to mention that part earlier. But looking at our problem here, we have 2x e to the x plus e to the x times x squared minus 3. There's no areas in this problem where it's going to be undefined. We're not dividing by any variables. There's no variables inside an even root. There's no variables inside a logarithm. So there's no way that this can be undefined. So we're just going to look at the points where it's going to equal 0. Now, the easiest way to set a binomial equal to 0 is to make sure you factor it first. I'm just going to rewrite that right away just because it looks nicer. So instead of 2x plus x squared, I'm going to write x squared plus 2x. Okay, now it's factored. Now we can set both of these equal to 0 and solve for x. So we have e to the x equals 0. Alright, e to the x equals 0. That will never happen. We can't raise e to some exponent and get 0. So we don't have to worry about that right now. X squared plus 2x minus 3. That's easily factorable. Whoops. So we get x equals negative 3 and x equals 1. So these are two critical points. So now I'm going to set up my number line. We have negative 3 and we have 1. Those are our critical points. So now we have 3 intervals this time. We have numbers to the left of 3, in between negative 3 and 1, and after 1. Alright, so now I'm just going to test some numbers. I'm going to first test this interval right here. So I'm going to pick a number that's less than negative 3. I'm just going to test negative 4. We're going to plug that into the first derivative, and if it's negative, it's decreasing. If it's positive, it's increasing. If you plug negative 4 into the first derivative, you would get a positive number. Okay, let's try the next one. We're going to do f of f prime of 0. If you plugged in 0, you would get a negative number. And then last but not least, let's just try f of f prime of 2. And again, you would get a positive number. So we went from positive to negative to positive. So if we go from positive to negative, that means our function's going up, then it's going down. Then if we go negative to positive, it means we're going from down to up. So that means we have a, let me change my color. We have a relative min. Whoops. A little sloppy there. At x equals 1. And a relative max at x equals negative 3. Again, local and relative are pretty much interchangeable. So there we go. We just found the local minimum or maximum of the function using the first derivative test.